Um, oh, fonts problem. Okay. So we can do the same kind of thing for quantum correlations. So these question marks were supposed to be a curly H for Hilbert space. So we've got to have a state in a tensor product of two Hilbert spaces. And for each value that X takes, there's an orthonormal basis of the Hilbert space A. And for each value Y, there's an orthonormal basis to the Hilbert space B. And then the observed correlations are just given by the usual Born rule in mod squared and in products. And then the block universe model for this is going to have our latent variable having two lambdas, lambda 1 and lambda 2. Lambda 1 takes values in the set of states that correspond to the measurement outcomes for LS, so all of them, for all the values of X and all the values of A. And similarly for lambda 2. Prior probability distribution is again going to be uniform, and the states will be prepared. So this probability here will just be the Born rule probabilities over our hidden states. And then as before, all that these conditional probabilities do is they copy the right state into lambda. Okay, and that is very straightforward to see that will reproduce the quantum predictions. So I'm not claiming that these are great models. I'm just trying to demonstrate that you can reproduce the predictions. Okay, so I'm not going to say anything at all about the general formalism, but I just want to mention that it's possible to generalize the lambda mediation assumption to any causal scenario you like. What we have here is, if you imagine, so we have regions of space-time which can hold a controlled variable, or they can hold a controlled variable and an observed variable, and lambdas mediate the correlations, right? So the lambda mediation assumption here would be, for instance, this set of variables here is conditionally independent of everything else given lambda 2, because to get from here to anything else, I have to pass through lambda 2. So you have assumptions like that. It's very similar to what you do in Markov networks and in factor graphs, although it's slightly different from both of them. And then you can prove from that that you get a decomposition where, if I have just a controlled variable in a region, I just get the probabilities of lambdas given, the incident lambdas given that controlled variable. And if I have both controlled and observed variables, then I get a conditional probability of the observed variable and the lambdas that are incident, that are connected by an edge, given the controlled variable divided by the probability of the lambdas on the neighboring vertices. Okay, so that's a general structure that you can get, and it shows that if you have the lambda mediation assumption, then it's not a complete free-for-all. You can't in a general causal structure, you can't reproduce any probabilities you like in this kind of framework. Okay, conclusions. So I've gone a little bit over time, so let me be quick. So we can make sense of causality in the block universe framework in a subjective interventionist sense, right? Whether there's some other notion of causality as well, it doesn't matter too much from the perspective of the framework here, but we can discuss that. When we drop the measurement independence assumption, but still keep the idea that lambda should mediate correlations, we do get a non-trivial structure for the theory. It's not that you can, when you get rid of measurement independence, you can reproduce anything you like. And we can generalize this beyond just the Bell scenario. So further questions, some of which I've worked on and some of which haven't. We want to know, to what extent can you evade the no-go theorems in this framework? So we've already seen that if we regard lambda mediation as the appropriate generalization of locality, then we have local models for Bell correlations in that sense. It's also possible to have models that are time symmetric in the sense of these no-go theorems that was started by Hugh Price, and then a follow-up paper by myself and Matt Pusey. There was a no-go theorem about time symmetry. That one you can get around. There still have to be some kinds of contextuality you can prove. I can discuss that in the discussion if you want. I don't know anything about whether there are psi-epistemic models in this framework. So you have to be a bit careful with this question, because if you look at this model, the state psi that you prepare is not ontic, it's not part of lambda. But Quantum mechanics has both a predictive formalism where you evolve states forward in time and a retrodictive formalism where you evolve states backwards in time. And the retrodictive state is real. It's the measurement setting states in this model. Okay, so I wouldn't call that psi epistemic because the retrodictive state is real. So that's an open question. I haven't really looked through the existing models. So models that violate measurement independence and just talk about superdeterminism or retrocausality in general, how many of those models actually satisfy this lambda mediation requirement? I don't know. I would view that as a requirement for a reasonable theory. And then of course, we have to explain in terms of this framework, I mean, this is very speculative to think that perhaps there is some kind of thermodynamic explanation we can come up with for why there's no superluminal signaling and backwards in time signaling in this framework. Okay, I'll leave it there. Thank you for your attention.
Yeah, I'd just like to follow up on your point that there is still contextuality in the models you were talking about. Can you elaborate on that a little bit?
Well, I'm talking about, so, I mean, it's kind of like easy to see why there is some kind of contextuality. So I'm talking about in the generalized sense of Rob Speckens, right? So there you say, okay, if you have two operationally equivalent procedures, then the description of them in the underlying model should be the same. And so it's very easy to see that if you have any retrocausality at all, you immediately have a type of contextuality, because here are two things that are operationally equivalent. Make measurement A and then throw the system away. Make measurement B and then throw the system away. Like, don't record the measurement outcome, just throw it away. Those are operationally equivalent.
Right.
You know, the thing only has one outcome. But if there's retrocausality, then there's information in the ontic state about whether you measured A or B, right? So there has to be, because otherwise there'd be no retrocausality, right? So any model for the Bell experiments that's local, of course, is going to be retrocausal and hence contextual in that sense. However, what's not clear is that every single proof of contextuality that applies in the standard framework works here. So there may be some kinds of contextuality that are present in standard ontological models that aren't present here. And I suspect that's true in the case of things like the Perez-Mermin square, because that kind of contextuality, I mean, I haven't worked out, I'm trying to work out the details of a model which handles what's called stabilizer quantum mechanics. And I believe it's true that you can have a appropriately non-contextual model for stabilizer quantum mechanics in this framework, but just not all. So that's a type of contextuality that I don't think you need in this framework, but there are types that you definitely have to have.
Thank you.